So in today's lesson, we are going to be covering orbital potential energy, and this entire presentation is themed around the video game Halo. The physics still apply here, even though it is a science fiction game, but it's just kind of to spice up the examples and just to have a more fun time with this. So, we know about potential energy formulas. The one that is used for most of high school physics is potential energy is equal to mass times gravity times height. And this formula works for the most part, but it's only a good approximation for at-surface calculations. So for example, like this ship right here, it's kind of just hovering maybe a couple 100 feet off the ground. So potential energy is equal to mass, gravity, height. Yeah, no problem for these type of questions, where it's just kind of like still in atmosphere. It's just kind of like it's like high, like maybe like a skyscraper or something like that. Anything along those lines. A more accurate version of this equation is potential energy is equal to negative gravitational constant multiplied by the mass of the first object multiplied by the mass of the second object, all divided by the radius between the two objects. This is a much more accurate formula and is used for outer space calculations. So for example, this alien ship here that is a couple thousand kilometers off the surface of the planet, so it's kind of in orbit in space. Using this equation is a much more reliable thing than compared to this equation right here. And if you've noticed this equation here, you might have noticed the negative sign in front of it. As it is negative gravitational constant mass over radius. So there's an actual reason behind this. So we know that the universe is infinitely expanding along all of its borders. So we know that we can just assume that the edge of the universe would be infinity, as it is forever expanding. So if you plug that into our equation here, so let's assume there's one object on this side and one object on this side, and the radius between them is infinity, as you know, edge of the universe. So just any object to the edge of the universe, the distance would be infinity. So let's plug that in there. So the radius in this case would be infinity. So negative gmm over infinity, and we know that anything divided by infinity is more or less just equal to 0. So if there is an object like here, and there's an object at the edge of the universe, the potential energy between them is 0, right? Because of the infinity at the bottom here. So we know anything less than infinity would cause the value to become negative, because if infinity is the highest possible radius between two objects, anything less than that would result in a negative number, because anything less than 0 would be a negative number, right? And 0 would be the answer to this here, because anything divided by infinity is 0. So anything less than infinity would therefore produce a negative number, hence the negative symbol. So we're going to get negative values for most potential energy equations. So let's head on to the first example here. In this first situation, we have a frigate that is at rest and it blasts off to a height of 2,000 kilometers above the Earth's surface, and they're telling us to find the potential energy and the work done by the frigate's engines. So as you can see here, we know the mass of the frigate, we know how high it is above the Earth, and we need to figure out the potential energy. So the first thing we need to do is identify all of our variables. So first we have G, our gravitational constant. This is going to be the same number every time. It's going to be 6.67 times 10 to the negative 11. Our next variable, the big M, doesn't really matter. These ones can be swapped interchangeably as long as like you just choose one, but for the most part, the big M is just a heavier object. So there should be two objects in this calculation here, and as you can see in this example here, there is two objects. There is this planet right here and the frigate right there. So the mass of Earth is 5.98 times 10 to the 24 kilograms, and the mass of the frigate is 12,500 kilograms. So we're going to plug that in there. So the first M is going to be the mass of the Earth, and the second M is going to be the mass of the frigate. So now we've identified G, M, and little m. The next thing we need to do is identify the radius. So we know that it is 2,000 kilometers above the Earth's surface. But that's not our radius. Our radius is supposedly supposed to be from center to center. And as you know, the Earth is relatively thick. So we must calculate it center to center from the object. So we know that it's going to be 2,000 kilometers above the Earth's surface. Hence there, I switched it to meters right here. And we need to add that to the radius of the Earth. So from the Earth's core to its surface, which is 6.38 times 10 to the 6. So now we have our actual radius, right? So we're going to add those two numbers there. So we're just going to plug all of those into the equation, and it leaves us off with a potential energy final of negative 5.95 times 10 to the 11 joules. And notice how it is a negative value here, from as proven by why it was negative in the last slide. So the second part of this equation is they are asking for how much work is done by the frigate's engines to do this. So we know that at the surface of the Earth, it's not moving, and we know that when it gets up here, it is no longer moving as well. That will be important for later. So for now, when we're calculating work, we use the work energy theorem. So change in kinetic energy plus the change in potential energy is equal to work done. So let's figure this out here. We know that it is at rest on the surface of the planet and at rest in space. Therefore, there is no kinetic energy in this equation here because, well, it has stopped moving and it was not moving. So we need to figure out the potential energy final and the potential energy initial. We just calculated the potential energy final over here, so we're just going to plug this value into here. And to calculate the potential energy initial, we're going to use the same values: gravitational constant, mass of the Earth, mass of the frigate, same as always, except this time the radius will just be the radius at the surface of the Earth, because initially it's kind of just resting at the surface. It's not 2,000 kilometers in the sky yet, so the radius is just going to be from the center of the Earth to its surface, or 6.38 times 10 to the 6. So calculating all of that, that will leave us with 1.87 times 10 to the 11 joules as our change in potential energy. And since there is no change in kinetic energy, work would just be equal to that change. So work would be equal to 1.87 times 10 to the 11 joules. And that's how much work the engines would do to move it from here to here. Now, these type of questions don't have to always involve some sort of heavenly body. So no, like stars, planets. This could just be between anything. This could be between me and my computer screen. This could be between like a bee and a dog. It could be between my fan and a window of my neighbor's house. So to show this question here is asking for the potential energy between this Covenant space station and this Covenant carrier ship. So we know the mass of the space station and we know the mass of the carrier. And we also know that the radius between them is 1,000 meters, center to center. So we don't need to worry about like the internal radius of the space station or this. We just know that from center of this space station to the center of this spacecraft is just 1,000 meters. So we don't need to worry about adding anything. So we know the gravitational constant. We know the mass of the first one, which is 1 times 10 to the 17. We know the mass of the second one, 2.7 times 10 to the 12. And we're going to divide that by 1,000 meters. So then that leaves us with a potential energy of negative 1.8 times 10 to the 16 joules. So as you can see here, Doesn't need to be a heavenly body. This is just between a spaceship and a ship, so more or less could just generally work with everything. So in this third situation over here, if you remember from the first example, we know that the object is at rest on the surface of its planet and at rest when it's in space. But in order to get into stable orbit, so kind of like this ship here where it's orbiting the planet, kind of like the moon does, it's moving. So there is a kinetic energy final. So in orbit equations, kinetic energy is equal to negative 1/2 potential energy. We know that potential energy is equal to negative gravitational constant mass divided by radius. So if we just plug this into this, we can get kinetic energy is equal to gravitational constant mass divided by 2 radius. So let's get our work energy theorem again. Because we are calculating work, we're trying to figure out how much work the ship's engines have to do in order to get into an orbit. So we know that the kinetic energy final has a value. We know the kinetic energy initial does not, because it's at rest at the surface of the planet. It's not moving, so no kinetic energy initial. There is a potential energy final, and there is a potential energy initial. So let's convert all of these variables here into their equation forms. So kinetic energy from here, we have potential energy final right here, and we have potential energy initial right here. So notice how the potential energy final kind of like swaps signs here, kind of just because potential energy is negative, so you know, positive negative makes negative, and we know that subtracted by potential energy final, so negative and negative, that's going to make positive in the end. So we're going to have, notice how these two here, we can actually subtract the two, because this one is kind of just like half of GMM over R final, and this one is subtracted by 1/2 GMM over R final. So that's going to leave us with negative 1/2 GMM over R final. And we know that the negative and negative will make positive, so we're going to add plus GMM over R initial. We're going to plug in all of our values, so the gravitational constant, the mass of the first object, the mass of the second object, and oh, this should be 10 to the 10, so don't worry about that. That's just a formatting issue. So that's not 1.1 times 1010. That should say 1.1 times 10 to the 10. So just don't worry about that. It's just a formatting issue. But regardless, we have GMM, so we're going to plug that to both of them because the top should be exactly the same. So now we have R final over R final and R initial. So radius final, we know it has an orbital radius of 2.6 times 10 to the 7 meters, which means the center to center has already been calculated. We don't need to worry about adding anything to that. So it's going to be that. And we have to remember that there is a 2 here, so it's just going to be 2 times the orbital radius. For our initial, we know that's at the surface of the planet, so we're just going to use the radius of the planet. So from the center of the planet to its surface, which is 6.38 times 10 to the 6. So we calculate all of that, and that leaves us with 6 times 10 to the 17 joules, and that's how much work the engines would need to do in order to put it into a stable orbit. In this fourth situation, we have a 300 kilogram drop pod, and it's released from a ship 6.3 times 10 to the 6 meters above the Earth. How fast will it be when it hits the ground? So we're just going to ignore air resistance for this, but for the most part, to get a feel for what this would actually look like, as you can see here on the right, that is a drop pod, and it would be dropping from a ship. And it would be hitting, like landing on the ground, so.
Could we possibly make any more noise? I guess so.
So as you can see there, kind of just not shot from space, kind of just released from space and landing on the surface of the Earth. So we're going to be using work energy theorem again, but this time there is no work because obviously you're just dropping something, right? There's no work to be done as all of the work is done just by gravity. So we know that change in kinetic and the work energy theorem states that it's just the change in kinetic energy plus the change in potential energy. We know that the kinetic energy initial is 0 because it's kind of just being held there by the ships. It's not moving, right? So it's not moving initially, at least. So for the most part, we can just kind of rearrange the equation here. So as you can see here, kinetic energy initial plus kinetic energy initial is equal to potential energy final plus kinetic energy final, and we can get rid of kinetic energy initial. So we're going to convert all of these numbers here, or all these variables here, to their equation form. Since we're looking for how fast it'll be when hitting the ground, we're going to be using 1 over 2 mv squared for kinetic energy final, because we need to isolate for that velocity there. So we know that negative gmm over r initial is equal to negative gmm over r final plus 1 over 2 mv squared. So we know that each one of these has a value for small m, or in this case small m being the drop pod. So we can actually cancel out all m here. We can cancel out this m, and this m, leaving us with this equation right here. Negative gm over r initial is equal to negative gm over r final plus 1 over 2 v squared. So isolating for v would leave us with this equation right here. So just the square root of negative 2 gm over r initial plus 2 gm over r final. So plugging in all of our values here, we have the mass of the Earth, we have the gravitational constant, and we have the two radiuses being initially being high up above the ground, 6.3 times 10 to the 6 meters. We're going to add that to the radius of the Earth, obviously, because this is not an orbital radius. It's just kind of above the Earth's surface. So we're going to add that to the radius of the Earth right here. And in this case, this is our R initial because it is starting high up. And our R final here, which is 6.38 times 10 to the 6, which is just the radius of the Earth because it has now landed on the surface of the Earth. Calculating all of that, that leaves us with a final velocity of 7,882 meters per second. And notice how small m gets canceled out. So regardless of the weight of the object dropping, the speed will be the same. So this is a 300 kilogram drop pod. If I dropped a 1,000 kilogram drop pod, the value would still remain exactly the same. And those would be all the examples for orbital potential energy. So thank you for listening to this presentation. And yeah.